So this is where we are in the droplet burning problem, where we got the solution for beta, which is the Schwab-Zel'dowicz coupling function in terms of alpha t and alpha o, the thermal the enthalpy, and this is the oxidizer mass fraction in the ambience. In terms of psi, where psi is actually a non-dimensional radius, which is actually the inverse of radius, like as radius increases, psi is going to decrease. Okay, and then we are looking for boundary conditions and also an interface condition, because psi involves this m dot which is unknown, and that's what we are trying to find out. So the first thing that we want to do is to actually look at the interface flux boundary condition at the droplet surface, and we are trying to actually form beta, which means we have to look at what happens to alpha t and alpha o. What we are doing here is to actually look for what happens to alpha o. So if you now look at what happens to yo divided by wo nu o will give you what happens for alpha o, and then we need to look at what happens to alpha t, which means we have to look at a energy flux balance at the droplet surface interface, right? So as far as that is concerned, if you now look at, so this was basically a mass balance at the droplet surface based on convective flux and a diffusive flux. As far as the energy balance is concerned, what we can understand is, now if heat conducted into the droplet must be just sufficient, and I'll explain what is meant by just sufficient pretty soon, but sufficient is what we should start with. Sufficient to vaporize the fuel leaving the droplet. That is to say, if you now have a flame with a flame temperature and then the heat gets conducted inwards, radially inwards, the heat conduction flux at the surface should be equal at least to the rate at which the heat is required for it to vaporize, right? And that is what is meant by saying just sufficient or at least sufficient. That is to say, if you have excess heat that is being conducted, part of it, in fact bulk of it, is going to be taken by the latent heat of vaporization to vaporize the droplet into vapor, and then you will have a further temperature gradient for the temperature to vary within the droplet. Okay. Now if you think about very small droplets, what happens is you have a very quick thermal equilibration that happens within the droplet, so the droplet is nearly at pretty much the same temperature everywhere within, with hardly any heat flux that is going on, because if you don't have any temperature gradients, you don't have any heat fluxes. So essentially the droplet is looking forward to only that much heat that is by conduction that is required for it to vaporize. Okay, and that's a kind of equilibrium that's attained, and this is reasonable. So what this means is 4 pi r squared k dt by dr at r equals rl is equal to m dot l. Now this is in some sense very similar to the convective diffusive balance that we have gone through. This is the diffusive part, this is the convective part, except what's important here for you is you have this is simply a m dot times yo, okay, that is like the mass flux of the oxidizer that is convecting inward in the space that is vacated by the droplet regression. Okay, that's what this dictates, but here this convection is actually based on the latent heat of vaporization. Okay. So in other words, you need to have latent heat of vaporization times the rate at which the droplet is regressing, or which is the same as the rate at which the gases are issuing out of the droplet surface. So this is pretty much the same. Of course we are neglecting a few things here, neglecting radiation. That's a significant effect wherever you have phase interfaces. We notice this when we were adopting the Schwab-Zeldovich formulation with the 11 assumptions, and we did neglect the heat flux due to radiation, and then at that point we noticed, or we pointed out that radiation can be neglected in a homogeneous system but not in a heterogeneous system. Heterogeneous system meaning when you have multiple phases, okay, physical phases. So here we have a phase interface between liquid and solid gas where radiation could be pretty important, but of course we neglect it for simplicity. So neglecting radiation and kinetic energy, we are not worrying about this little kinetic energy that we are going to have for the vapors that are coming out at a certain velocity because of the droplet regression. That is significantly small, so this is reasonably okay to neglect it. Now L of course is the latent heat of vaporization. Latent heat of vaporization per unit mass of the fuel. At temperature at TL, let us say that is the droplet surface temperature, TL as I said, if the droplet is reasonably small and you have a thermal equilibrium within the droplet, the temperature is going to be pretty much the same at TL. Whatever is the surface temperature is going to be the same uniformly throughout within it. At the moment we are not really interested in what's happening within the droplet, and that is the reason why we are assuming this just sufficient. That means we are not going to have any further heat conduction after the latent heat has been removed. Okay, so now let's of course we have Lewis number L equal to 1, which is K over rho Cp d, and of course the other thing that we also do is take T naught equal to TL for convenience, and this is not very difficult to swallow because we have seen this before. If you now take a different value and then we still insist on T naught, you can have two integrals, and we find that these things are actually showing up wherever you have alpha t or beta showing up. It's all in derivatives, therefore a constant addition is not a problem. So we can do this. So therefore this condition then is now going to translate to, because we can now take, for example, take the m dot down here, and then K can be replaced by rho Cpd, right? So you replace K by rho Cpd, and of course Cp can be stuck with the temperature, and then you have 4 pi r squared rho d divided by m dot coming from the other side, and then we look at how psi is defined, and keep noting that 4 pi r squared rho d is in the denominator, and the way psi goes is inverse of rho. So we should, for example, we got a negative sign here, right? And similarly, when you now try to write this in terms of the non-dimensional independent variable psi, you should have a d by d psi of integral T naught to T Cp dt equals minus L. That's the reason why you got the negative sign. So if you now try to say, I will divide this by Q and this by WO nu O, which means I go back and divide this by WO nu O and this by Q, I will have, wherever I have a YO, I will have a alpha O, and wherever I have integral T naught to T Cp dt divided by Q, I will have a alpha T. Then subtract one from the other to get alpha T minus alpha O, which means we get the beta, right? So putting the two flux balances at the droplet interface together, we get d beta by d psi. Of course, I should go back and write this at L. So d beta by d psi at L equal to minus L divided by Q minus YO L divided by WO nu O. All right. All right. Now this is the interface condition. In addition to this, we need to have the regular Dirichlet boundary conditions, right? So the Dirichlet boundary conditions at the boundaries to the domain are the Dirichlet boundary conditions domain R, we should say at R equals infinity, psi equal to 0, okay, at R equals infinity, psi equal to 0, right? And what would that mean? We would say, what would be a beta? A beta would be whatever is alpha T and alpha O at R equals infinity, which means whatever is the temperature T infinity, right, at far away, and whatever is YO infinity. So for example, if you have air as your ambience, your YO infinity will be like 0.23, because only about 23% by mass is going to be oxygen, the other one, the rest is going to be nitrogen. So you have a diluent present in your ambience, in your oxidizing ambience, which can be taken into account. You can also take into account the ambient temperature, and keep in mind, if we don't have to worry about a combustion heat release, then we could still solve the evaporation problem if your T infinity is higher than TL. All right, and that is going to basically mean that you have heat conduction simply from the ambience, not necessarily from the flame. Okay. So the T infinity is going to play a role, and as a matter of fact, this is actually the sensible enthalpy term, and this is the heat release term. So this is already showing up as a competition between the two. Okay, so we will see these things a lot more clearly as we go along, but essentially what it means is beta can be equal to beta infinity, which is alpha T infinity minus alpha O infinity, which is nothing but T naught to T infinity Cp dt divided by Q minus or should I say plus YO infinity divided by WO nu O. That's the one boundary condition. At R equals RL, we are kind of coming inwards, because that's how psi increases from 0. So psi is now going to be equal to some psi L, which is saying psi L is equal to RL, integral RL to infinity, right? And so psi L, and beta will have some value beta L, okay, which is nothing but alpha T L minus alpha O L, which is integral T naught to T L Cp dt divided by Q plus YOL divided by WO nu O. We have already seen that if you now take T naught equal to TL for convenience, this wouldn't have any contribution, but that's all right. Let's just at the moment worry only about beta L. Let's not worry about how it is exactly defined. We will ultimately see that what matters is not exactly each of these, but beta infinity minus beta L, in which case we can now put these things together, and these integrals will now go together, and then you will get an integral goes from TL to T infinity. Okay, so the T superscript naught gets out of the way anyway. So good. That means we are now ready to attack the solution better. We were armed with these, so let's do one by one. So let us say, how do I number this? yeah, I think I should mention what is psi L here for the record, where psi L is m dot integral RL to infinity 4 pi r squared rho d to the negative 1 dr. Okay, and I think we should probably call this as 2, right? So we call this as 1, and okay, now so the first thing we can do is at r equals RL, beta L equal to a plus b e to the minus psi L at r equals infinity, beta infinity is simply equal to a plus b, because psi equal to 0, so e to the 0 is going to be 1, and subtract to get rid of a, and actually, you know, by now you should get the idea of what the drift is. We are not really interested in solving for alpha, I mean betas at all. Okay, that's not really our problem. Our problem is to find psi L, so that from psi L we can get an idea of m dot, and m dot is what we are basically looking for. We are not looking for the actual profiles. So the real problem is what is the rate at which the droplet is shrinking. Okay, everything else is a detail, and so we will solve we will keep our focus on the problem. All these details, like how exactly beta is varying, that means how is the temperature going to vary, how is oxidizer concentration going to vary, and all these things are all exam questions, PhD qualifying exam questions and so on. Okay, so that's for you to figure out, but we will focus on our problem. That means at the moment we can just subtract these two, get rid of the a. We are not going to bother about evaluating it for ourselves, and we are simply going to get b equals beta infinity minus beta L plus b e to the minus psi L, right? That's true. So b equals beta infinity minus beta L plus b right. Then question is, what is beta infinity minus beta L? But beta infinity minus beta L is nothing but, you just have to, this is beta infinity, this is beta L, so this is beta infinity, this is beta L, subtract one from the other, so you get sigma k equals 1 to n yk infinity integral TL to T infinity CPK dt. That's a fancy way of writing CP. Simply you could have taken the yk inside, and but we want to show the infinity very clearly, divided by q, and the reason why we are not really worrying about ykl is because, as I said, here if TL is equal to T naught, this is not going to contribute, right? And plus yo infinity minus yol divided by wo nu o, right? So that's what we get. Then we have to use the interface condition. So what we have now is, we have b is equal to this plus b e to the minus psi L, with which you can evaluate b, all right, but we are not really bothered about, as I said, evaluating b. We are not interested in evaluating a as well. We are not interested in finding betas. What we are really interested in is to apply the interface boundary condition so that we can even eliminate b. Okay, so fortunately The interface boundary interface flux condition put together in terms of beta has it in terms of derivative. So if you have it in terms of derivative, A automatically drops out. You try to take a derivative here, A doesn't even show up, B shows up, okay, and between that and this we will eliminate B as well, okay, that's it, that's what we are going to do. So using the interface flux balance, right, we get B e to the minus psi L equal to L over Q d beta by d psi is going to have a minus B e to the minus psi, right, and evaluated at L, right. So we should have a negative sign, but they also had a negative sign here which I am going to turn it as positive, right. So we now have this as L over Q divided by to plus YOL divided by WO nu O. Now if you call this as your 3, I guess this is your 3 and this as your 4, then what you do is we now use 4 and we now use 4 and 3 together in order to get e to the minus x psi L and use what is the definition of psi L, okay, that's what we do. So putting 4 and 3 together and using 2, right, we get psi L equal to natural logarithm. We got the natural logarithm because between these two, if you now try to get rid of B, you will be working with e to the minus psi L, okay, and if you now try to extract psi L out of it, you will get a natural logarithm, okay. So natural logarithm of 1 plus sigma k equals 1 to n yk infinity integral TL to T infinity CPI dt divided by Q plus YO infinity minus YOL divided by WO nu O. So that's coming from here divided by L over Q plus YO L divided by W nu O, that's coming from here, okay. And this 1 plus was coming because you had a B and a B there, so you could have a 1 plus. So that's the mathematics, and then in this you now use 2 because psi L has this definition, so you now get in dimensional form m dot is going to be 1 over integral RL to infinity 4 pi r squared rho d to the negative 1 dr natural logarithm, just for the record got to write the whole thing again, 1 plus sigma k equals 1 to n yk infinity TL over T infinity CPI dt divided by Q plus YO infinity minus YOL divided by WO nu O divided by L stop. We could do a little bit of manipulation. If you now try to multiply Q throughout both numerator and denominator, you could write this as plus Q, and this would be plus Q YOL divided by WO nu O. Of course, in the final videos we can edit out this time it took for it to write, okay, and then we can just show the final expression written again, and here we will basically point out that we have multiplied the numerator and denominator throughout by Q, so that the Q shows up here and here instead of at the bottom of this and this. So that's the final expression for m dot, and as usual we don't understand this. Okay, so we get some complicated looking expression which just doesn't make sense. We started out thinking we wanted to get the d squared law. Okay, the d squared law is essentially saying that if you now are looking at the rate at which the evaporation happens, the time of evaporation is proportional to square of the diameter. Okay, and we notice that the square of the diameter is going to be sort of like the surface area, and we also then notice that if you now look at the m dot, the mass flux, the square of the radius shows up, which means the square of the diameter shows up, and this in fact is the surface area, 4 pi r squared, or L squared is the surface area of the droplet. So all that seems okay, and now we got an m dot. How in the world are we supposed to get the d squared law from this? Okay, so or how are we supposed to now find out how the d squared varies with time for the droplet regression? Okay, we have adopted a quasi steady assumption by which in the instantaneous snapshot at a particular time the m dot is like this without any time dependence any further. Okay, and the time dependence that we have gotten rid of is the small time scale that it takes for the gases to diffuse and convect at a particular snapshot freeze frame time, and from this time for you to get to the next time when the droplet regresses significantly takes a lot of time, and then we will now look at the picture now and then do this balance and then figure out what the current m dot is and so on. That's what we are trying to do. So if you want to try to understand this further, it'll be helpful if we do some more simplifications. Okay, so let's try to do that. So let's try to do some simplifications here. The first thing that we will say is YOL is approximately equal to 0. That means we are saying that the droplet, the oxidizer as it diffuses all the way to the droplet surface is pretty much of zero concentration, or put it another way, all the species that you have at the droplet surface is going to be mainly fuel vapor. So if all of it is going to be fuel vapor, it has completely displaced all oxidizer, so you don't really have any oxidizing species. This is one way of looking at it in a mostly evaporation situation. In a combustion situation, it's a lot more convenient because we expect that the fuel vapor and the oxidizer vapor are going to diffuse against each other radially and meet at stoichiometric proportions where the flame is and then get consumed there, right? So if you now took a magnifying glass and looked at this particular sheet, we should now be able to find out how these things gradually decline. The oxidizer, the fuel concentration gradually declines up to this flame and then rapidly declines because of consumption, and the oxidizer concentration gradually declines as you go radially inward because of diffusion and then rapidly decline across the flame, right? and therefore at the droplet surface you're not going to get any oxidizer at all. So YOL can be assumed to be more or less 0 without much of a problem. The exception, see, any time you make a assumption which is simplifying, you have to look at how good it is, okay, or when would it not be held, and the answer is this is not really quite true near extinction conditions. That is, when the droplet is going to actually extinguish, right, you have a rather weak flame and you have ample opportunity for the oxidizer to diffuse past the flame in spite of going through reactions and getting consumed quite a bit, because it's not getting completely consumed, right. So this is mostly true particularly in combustion situation, except near extinction conditions. So that's one simplification. What would that give me? That will get rid of the YOL here, right, that will get rid of the YOL here. So it's kind of like we could send this to a hairdresser and get it to be nicely dressed up and look like a very simple expression, right. So that we're trying to get rid of some of these terms that way. Let's also assume that TL is equal to TB, which is the boiling point of the liquid. That's a simplifying assumption. In reality we have to actually look at something called a saturation temperature and so on, which depends on the ambient what do you call ambient composition of its vapor and so on. So you have to look at vapor pressure, balancing the actual pressure and all those things. Now let's not worry about all that. We'll simply say TL, the droplet temperature, is going to be the same as the boiling point, and let us assume that rho d is a constant which is equal to k divided by Cp, okay, because L equal to 1, and suppose Cpi equals constant equals Cp. All Cp's are the same and it's constant, right. So make these assumptions, and what do you have? We get, so with which we can now try to evaluate this integral also, right. So rho d gets pulled out of the integral, and you can integrate dr divided by 4 pi r squared, right. That's not a problem, and then substitute the limits. You get m dot equals 4 pi k RL over Cp, that's what rho d has now become, times natural logarithm 1 plus Cp. You can now evaluate the integral inside as well, as simply T infinity minus Tb plus Q YO infinity divided by should say we have a WO nu O divided by L, right. Okay, you still have some expression, but this is a little bit more manageable. We can try to understand something more. Let's just think about it for a minute. Okay, what this means is this is the sensible enthalpy, okay, for the gas going from the boiling point of the droplet to the ambient temperature. So this is the sensible enthalpy rise of the gas that's coming out of the droplet. This would actually be corresponding to the heat of combustion. So for the moment let's not worry about the heat of combustion, okay. Let's suppose that we are thinking about evaporation. That means you have an ambient hot gas that is trying to evaporate the droplet, and that means it is simply giving rise to a sensible enthalpy rise by L. So the L is what is actually is the latent heat that is required first of all for you to vaporize, and then the next thing is you have to raise the sensible enthalpy. Okay, so the m dot is dictated by how much you are able to evaporate versus how well you are able to rise the sensible enthalpy of whatever we have evaporated. If you now throw in combustion, you now have this term in addition. Okay, so the heat that is available to you goes first to evaporate the droplet and second to raise the sensible enthalpy. Okay, so you can see how these three processes, essentially heat release that is available to you during combustion, can go on to raise the sensible enthalpy in competition with evaporating the droplet. Okay, so this is what is actually dictating this m dot. Now what we are interested in is in trying to find out what is the relationship between or how is this RL going to change in time. Okay, that's what we are really interested in. So for this purpose we can see that so notice that m dot is now linearly proportional to RL, right? So say m dot equals k prime RL. The reason why we are using k prime is k is reserved for the evaporation constant in the d squared law, and that's what we are trying to deduce. Okay, we are trying to deduce the d squared law, and therefore we want to see what is the dependence of the evaporation constant on the system parameters, namely like the ambient gas composition, ambient gas temperature, the boiling point of the liquid, the latent heat of the liquid, and so on, right? So we want to know what the k is, and so we now keep this as a k prime. So where k prime is equal to, except RL we have to write everything else, which is 4 pi k divided by Cp natural logarithm 1 plus Cp T infinity minus Tb plus Q yo infinity divided by wo nu o divided by L, right? So keeping that as a k prime, the next few minutes we are simply going to ignore all this stuff and going to basically say m dot is equal to k prime RL, and let's see what that means, right? So m dot on the other hand is negative 4 pi RL squared rho L d RL over dt, right? This t is now at the time scale of the droplet regression. It's not a shorter time scale of the gases equilibrating in diffusion and convection. So this is the kind of time that you're looking for in the d squared law. So this is now equal to k prime RL, which means we can now cancel the RL squared, one of the RLs in the RL squared with this, and from this we can now write RL dRL equal to negative k prime divided by 4 pi rho L dt, all right, and then just go back and write this with let's say RL naught to RL, any RL, starting from T naught to any T, and that's now beginning to show up as the d squared law. So this is 1/2 RL squared minus RL naught squared, or okay, let's just keep it that way, and we have a negative sign to fix things. So we have a 4 pi rho L T minus T naught, and of course now this negative sign will allow us to flip things because RL naught is actually greater than RL, therefore we want to keep things positive, and keep in mind RL is nothing but dl over 2, so RL squared will be dl squared over 4, and so the 4 and 2 are going to get together to make an 8, and then of course you have a 4 pi that's going to go away, and k prime also has a 4 pi, so don't be in a hurry to cancel that with the 8, okay. So dl naught squared minus dl squared is equal to 8k prime divided by 4 pi rho l t minus t naught. So now it's beginning to look like the d squared law. Boy, couple of minutes, about 10 minutes ago, this didn't look like the d squared law at all. Okay, but that's the d squared law there, and so we have the d squared law. So with the evaporation constant k, right? So what's the d squared law? Just for the sake of completeness, d squared dl naught squared equals k times t minus t naught, k equal to, so evaporation constant k, right, where k equal to, we just have to put things together, 8k prime divided by 4 pi rho l, and then of course you have a, so you just divide this by 4 pi rho l, and then throw in an 8, and you're simply going to get a 8k divided by rho l cp, natural logarithm 1 plus 1 over l cp t infinity minus tb plus q yo infinity divided by wo nu o, right. And as I said, all the dependencies that we are looking for are there in the evaporation constant. You can also use this for evaporation as well as combustion. All you have to do is neglect the heat of combustion, forgetting the evaporation. If you want to keep the combustion, then keep the heat of combustion, and you will get an additional evaporation rate. Okay, so that means because of the combustion it burns faster, it regresses faster. That's what it simply means. So with this we should stop doing droplet burning, and we will see what else we need to do next week.